we have dealt with energy and momentum of EM fields. And today what I am going to do is use these to define something called the center of energy of a system of charges and currents. This is similar to center of mass of a collection of masses. And then I am going to show you something called the center of energy theorem that says exactly like the center of mass, if the center is stationary, then the total momentum of the system is 0, and this momentum includes both the electromagnetic momentum as well as the motion of these charged particles. So, let us begin on this. So, just a recall for mechanical systems that total momentum P mechanical is given as m I v I for a system of particles, and from this we define something called the center of mass, which is given like this. So, V C m is equal to summation m I v I total momentum divided by the mass, and related quantity is R C m, which is 1 over m summation m I R I, or equivalently m R C m is equal to summation m I R I. And for isolated systems, V C m is a constant, because summation m I v I is equal to constant. Now, what we want to do is do exactly the same thing with charged particles moving, and therefore, there is a current also. So, here are these charged particles and they are moving, so that I have Q, J R and electric field and magnetic field, and the total energy of the system is equal to U electromagnetic plus U mechanical. I am using U because books use it. In our language, you can also call it E electromagnetic plus E mechanical, and I can define a quantity integral R U electromagnetic R, where U electromagnetic is the energy density in electromagnetic field integrated over the entire volume, plus summation R I and total energy E I mechanical as E total times R center of energy, and then we will prove the theorem. So, theorem would be just like the theorem for the masses. So, for a collection of masses, we have that m d r C m over d t is equal to total momentum. For fields and charges, we are going to have total energy E total times d r center of energy over d t is equal to c square times p total momentum electromagnetic plus p mechanical. As a consequence, if d r c e over d t is 0, that means the center of energy is not moving, that means energy is not flowing. This will imply that P E m plus P mechanical of the system will be 0. This is known as the center of energy theorem. And since electromagnetic phenomena automatically includes in it relativity, you will see that we have to define mechanical momentum also relativistically. Non-relativistically, this will not hold, and I will discuss that through an example. So, we start to prove this. We start with, remember, u E m by d t, d by dt of u electromagnetic, where u electromagnetic is the density of electromagnetic energy, plus j dot the electric field is equal to minus del dot S. We will start with this. Since I want to get R n, I will multiply by R. Let me first make a picture. Here is this volume, here is some origin O. I take a point at a distance R, small volume here, and this is where I have written the above equation. There is this J going through, and there is this electric field that exists. So, this is the energy conservation equation. Let me multiply by R on both sides and write this as d by dt of u electromagnetic R t multiplied by R. Notice that this R does not depend on time, it is the distance of a given point, plus R j dot E, where E is the electric field, is equal to minus del dot S times R. So, let me write what different terms are. U E m R t is the energy density for E m fields that exists there. E is the electric field, and S is the Poynting vector. And now I will integrate. So, when I integrate u E m R t R d v, the time derivative I can take out, because only u is changing with time, plus j dot E R d v integrated over is equal to integration with a minus sign divergence of S R d v. I have got 3 terms. I will take j coming from point particles at that point. So, let me write this as q I delta R minus R I, that is the density, times V I, where q I is the charge on that charge carrier, times delta R minus R I gives me the density, and then multiplied by V I. So, that j dot E, or this is also being summed over at that point, whatever the particles are. So, j dot E is going to be equal to summation I q I delta R minus R I V I dot the electric field, where q I, the I that is being summed over is actually the number of particles there. So, I can write integration j dot E d v as equal to integration summation I q I delta R minus R I V I dot E dV. There is a R also somewhere, there is a R also here. So, this gives me summation I Q I V I dot E R I. I can therefore write this equation as d over dt of u electromagnetic R dV plus summation I Q I V I dot E R I is equal to minus del dot S R dV. dV is over the entire volume, and this now includes all the charges, because we have integrated over the entire volume. The summation runs over all the charges in the volume. So, notice the transition from j dot E dV R, which was integration R summation Q I V I, and this summation at that time was within dV dot E dV. Once I integrate, the transition is that this goes over to the sum I Q I V I dot E R I, and let me write this with a different color, over all charges in the volume. So, that is very important. Right. So, let us see what we have gotten now. We have gotten d over dt integration R u e m r t dV plus summation q I v I dot E r I is equal to minus integration divergence of S r dV. Let me now write different terms. Summation q I E dot v I r I is nothing but, this is the force on ith particle. So, force times v I is going to be d E I mechanical over d t r I vector. This is r I vector. This is summed over I, which is nothing but summed over I d by dt of r I E I mechanical minus E I mechanical V I summed over I, where V I is d r I over d t. That is number 1. Number 2, I will leave this for you. Show that divergence of S multiplied by R dV is equal to integration S dV. I am leaving this for you to show. It is exactly like what we used to do in the current. So, what we have now is that d over dt of integration R u e m r t dV plus d over dt of r I E I mechanical. I have made an error here, this should not be a vector on the left hand side, is equal to integration S dV plus summation E I mechanical V I. Let us write this equation on the next slide. So, I have got d over dt of integration R u electromagnetic R t dV plus d over dt of summation R I E I mechanical is equal to integration. Let me see if I made a mistake on the previous slide. There should have been a minus sign here. So, this is plus S dV plus summation I E I mechanical V I, which I can further write as d over dt of integration R u e m R t dV plus summation I R I E I mechanical is equal to, now I am going to say S is nothing but c square times the momentum density, which is referred to as G R dV, plus I am going to use relativistic expression. So, summation I m I c square V I over square root of 1 minus V I square over c square, where G R is nothing but epsilon 0 E cross B. This is the momentum density, and number 1, number 2 relativistic expression for energy is used. Left hand side by definition is nothing but E total times d by dt of R center of energy, where we are saying that the total energy remains the same, and this is equal to c square P electromagnetic plus P mechanical. So, we proved the theorem. So, notice I could write this because we will assume that E total is independent of time. If it were not, then it will remain inside, and R C E is defined as summation R I E I mechanical plus integration R u e m d v divided by E total. So, this is the center of energy theorem. So, what we have obtained is that given a system of charge particles, and obviously there is this electromagnetic field there, the total energy is conserved, and therefore, you can write that E total d r center of energy over d t is equal to c square times P total. If R C E does not change, which will happen if energy is not flowing or anything, this will imply that d R C E d t is equal to 0, and therefore, the total momentum of the system is 0. And when we say total momentum, this means P electromagnetic plus P mechanical 0. So, let us now illustrate this through an example. Example is, let us take a charge Q and a circuit next to it that has current I going through it. This example is taken from Zangwill's book. If I were to calculate the electromagnetic momentum, it will be equal to epsilon 0 integral E cross B dV, which I can write as minus epsilon 0 integral grad phi cross B dV. Now, I am going to use curl of phi B is equal to phi curl of B minus plus grad phi cross B, and therefore, P electromagnetic is going to be equal to epsilon 0 grad phi B with a minus sign. So, that is going to be epsilon 0 the minus sign curl of phi B plus epsilon 0 integral phi grad of B dV. So, what we have found is that given this charge Q and a circuit carrying current I have P electromagnetic as equal to minus epsilon 0 integral grad of phi B plus epsilon 0 integral phi times grad of B dV. I am leaving one problem for you. Prove that curl of a vector integrated over a volume is equal to minus the surface integral V cross ds, and use it to show that integral curl of phi B dV is 0. I expect you to show this, and therefore, I have P E m is equal to epsilon 0 integral phi curl of B dV, and by using Maxwell's equation, I have curl of B as mu 0 times phi j r dV. This is 1 over c square, and therefore, P electromagnetic is equal to 1 over c square integral phi j r dV, and this is not necessarily 0. Now, this is a system which is time independent, center of energy should not be moving. So, we know in this case that d r c e dt is 0, and therefore, P E m plus P mechanical should be equal to 0. So, I need to calculate mechanical momentum, and keep in mind that P mechanical is calculated relativistically. So, in the circuit, these charges are moving, and I want to calculate P mechanical for these charges. For simplicity, take all carriers to be identical, that is q is the same, mass is the same, and there is some velocity v I. Now, non-relativistically, P mechanical would be equal to summation m v I, which I can write as m over q summation q v I. This is all over the particles. So, this will become m over q integral j r d v. And you know from earlier exercises that integral j r d v is 0. So, P mechanical is equal to 0, non-relativistic. So, P electromagnetic plus P mechanical is not equal to 0. So, we got to do relativistic calculation, as I said earlier, then only this theorem applies. The difference between relativistic and non-relativistic momentum for these moving particles is sometimes referred to as hidden momentum of these particles. So, let us do now a relativistic calculation. In relativistic calculation, P mechanical would be equal to summation m, there is a gamma associated with each particle V I, which I can write as, I will multiply this by 1 over c square summation I m c square gamma I V I. M c square gamma I is for the ith particle the kinetic energy. So, I can write this as summation kinetic energy of the ith particle V I. So, I have written relativistically that P mechanical is equal to 1 over c square summation kinetic energy of ith particle. Notice I have already used the relativistic expression. So, this I can write as 1 over c square, kinetic energy of ith particle will be E mechanical for the ith particle minus q phi at that particle position r I v I. So, this has two parts. So, this is equal to 1 over c square summation I E I mechanical v I minus 1 over c square summation q v I phi at r I. Now, this part can be written as minus 1 over c square q v I gives me the current there. So, I can actually write this as integral j at r phi at r d v. So, this part gives me this. How about the first part? For the first part, if I take E to be the same for each particle, I get 1 over c square summation v I E outside, which I can write as E over c square q integration j r d v, which is equal to 0. So, I get P mechanical is equal to minus 1 over c square integration j r phi r d v. And recall that P electromagnetic we show to be 1 over c square integration j r phi r d v. So, P electromagnetic plus P mechanical is equal to 0. This is what was expected from the center of energy theorem. So, along the way I have made certain approximations to keep life easy. I have taken E to be constant for each particle. I have taken all of them to the same. Even if you put those ith particles, ith energy in, the answer would still come out to be the same, and this I will give you as an assignment. I will also give in the along with the lecture a reference for this. So, to conclude the lecture, we have proved center of energy theorem for a collection of charges. So, this tells you for isolated systems, the total momentum which is P E m plus P mechanical vanishes, and we showed this through an example. Thank you.